So today's class is on the refrigerant circuit or the refrigeration circuit, and then we're also going to cover superheat and subcooling. My name is Wade Hadaway. I am DTR in the Southeast. I've been with Ruud for a little over 5 years, and I have been working with Tropic for that same amount of time. Today is part 2 in the series, Wade's Words of Wisdom, we got 3 more classes. So after we finish up today, we'll do one on specifically heat pumps, right? Reversing valve, demand defrost. Then we'll do an airflow class, and then we'll do sort of a basic electricity class and electricity and basic wiring. If you participate in all 5 webinars, so those of you who were here 2 weeks ago and you're back, you're well on your way to getting a free copy of the heat pump service manual. If you've seen any of these service manuals, they are an invaluable tool designed to be carried with you in your truck or in your van to help you solve problems and diagnose and troubleshoot. There'll also be sort of 4 quizzes. We'll have 2 quiz sections during today's class. I'll ask 2 questions for each one. And whoever answers that question correctly first, so the first correct answer is going to win one of these prizes today. So we're going to talk about, like I said, the refrigerant circuit. We're going to talk about the major components. Now, I realize that there are a lot of other components in a refrigeration air conditioning system, but I want to really just sort of strip everything away and look at the major components. We're going to talk about the evaporator, the compressor, condenser, and metering devices. And we're going to talk about superheat and subcooling. What do they mean? How do we measure them, and why is it important, right? What is superheat and subcool telling us when we're looking at a system? And for whatever reason, I cannot get this menu bar to go away. All right. So in an AC system, we've got 2 sides to that system, right? We've got a low pressure, low temperature side. We got a high pressure, high temperature side. And the sort of dividing points between the low pressure, low temp, and the high pressure, high temp sides are the compressor and the metering device. So the compressor allows us to increase the pressure of the refrigerant, which we covered 2 weeks ago in part 1. As we increase the pressure, we're also increasing the temperature. And that's crucial, because if we can't get the temperature of the refrigerant well above the temperature of the outdoor air, we're not going to have that heat exchange, right? We covered heat moves from a higher concentration to a lower concentration. If it's 95 degrees outside and the refrigerant is not well over 95 degrees, we're not going to transfer the heat. So how do we do that? We change the pressure, which changes the temperature. And then, so as we're leaving the compressor as a high pressure, high temperature vapor refrigerant, we go into our outdoor coil or our condenser, and we change the state of that refrigerant. We pump it indoors. In a split system, we pump it indoors to our expansion valve or our metering device, where we have another pressure temperature change. So we drop the pressure of the refrigerant, which drops the temperature of the refrigerant, where we send that refrigerant traveling through the indoor coil, where we have to, we're going to pick up heat from the indoor air. And the only way to do that, the only way to pick up that heat is to make sure that the temperature of the refrigerant is well below the temperature of the indoor air. So if we've got a 75-degree indoor air, our temperature needs to be of the refrigerant needs to be much lower so that the heat will move from the higher concentration of the indoor air to the lower concentration of the refrigerant in the evaporator coil. And on the drawing, it says outdoor coil and indoor coil. Because in a heat pump system, our outdoor coil half the time is our condenser, and then when we switch to heat, our outdoor coil is our evaporator. So that's why the drawing says outdoor coil and indoor coil. So here is a graphic of an end coil, of an evaporator coil, and what's happening in this coil, right? As I said, it's a low pressure, low temperature refrigerant that is traveling through this coil, and it absorbs heat from the conditioned space. And if you remember from part one, we talked about the different kinds of heat. We talked about sensible heat. We talked about latent heat. The refrigerant that's flowing through the tubing in our evaporator coil is absorbing sensible heat and latent heat. It's absorbing sensible heat as it drops the temperature of the air that's flowing through the coil. And it absorbs latent heat as it dehumidifies the air, right? So we talked about dew point, and we talked about sensible and latent heat. As the indoor coil is below the dew point of the air that's flowing through it, that causes the moisture in the air that's flowing through the coil to condense on the fins of the evaporator coil, run down the coil into the drain pan and out our condensate drain. So we're absorbing two kinds of heat in the evaporator coil: sensible heat, latent heat. And while we're doing that, the refrigerant changes state from a liquid to a vapor. And we'll talk a little bit more about this when we get to the metering device specifically, because that's where it starts happening, right? So as the refrigerant is flowing through the evaporator coil, it's slowly evaporating or boiling off. And as we're changing the state of the refrigerant, that's where we're doing most of the work, if you remember from part one. So as we're removing heat from the removing heat from the air, transferring the heat from the indoor air into the refrigerant in the evaporator coil, it's slowly boiling off. And in that change of state is where we remove the most BTUs, right? That's where the lion's share of the work is done in the evaporator. It's changing state of the refrigerant. And the reason that superheat is important is because when we think about superheated refrigerant, that tells us what the condition of the refrigerant is as it's leaving that indoor coil or that evaporator coil. The refrigerant in all of the systems that we manufacture, the refrigerant has to be 100% vapor before it leaves the evaporator coil, because we don't want to send any liquid refrigerant to our compressor. So superheat is really the first thing it tells us is that we know we don't have any liquid, because the refrigerant cannot be superheated if there's any liquid refrigerant left in there. It has to be 100% vapor before it can be considered to be superheated. And a sort of simple definition of superheat is that the refrigerant is warmer than its saturation temperature. And I'll talk a little bit about exactly what that means, but we're taking the line temp of our suction line coming out of our indoor coil or out of our evaporator coil, and we're comparing that to the saturation temp, or what the pressure temperature relationship of that refrigerant tells us that it would be if there was a mixture of liquid and vapor refrigerant. So if you look at the table on the left, that is from the pressure temperature chart for 410, for R410. And the pressure temperature chart tells us that at 145 psig, the saturation temperature of that refrigerant is 51 degrees Fahrenheit. So this is where the saturation temperature comes from. You're not going to measure it other than measuring the pressure of that refrigerant and then seeing what the pressure temperature relationship is, right? You can also get that number from your manifold gauge. And that's where these rings on your gauge come from, right? So here's our pressure in the blue. Here's the saturation temperature at that pressure in the pink for 410. And like I said, this only applies when there is a mixture of vapor and liquid. It has to be saturated, meaning that there's vapor and liquid present. So the way that you would measure your superheat, right? So we already hooked our gauges up, and we've got 145 psig. That's our suction pressure. And we're measuring our suction line temperature. And it's very important when you're checking evaporator superheat, and that's how all of our charging charts are built, on evaporator superheat, not what we would call system superheat. So it's important when you're checking superheat that you take your temperature clamp and you put it at the suction line coming out of your indoor coil. If you're checking superheat at your outdoor unit, which if you've got a electronic gauge manifold that comes with two temperature clamps, and you clamp them on the outside, you're reading superheat, but it's system superheat. And the reason that matters is that suction line can continue to absorb heat depending on the conditions, right? If it's on a 150, 160 degree attic, that Armaflex does not allow, or it does not offer a lot of insulation. So you can pick up several more degrees of superheat. If you really want to know what your superheat is, you need to check at your indoor coil. So we got a suction pressure of 145. That gives us a saturation temp of 51 degrees Fahrenheit. And if we clamp our temperature clamp onto the suction line coming out of the coil, we can see that it is 61 degrees. And we're simply just gonna make a determination of how much hotter the suction line actually is than the PT chart or the pressure temperature chart says it would be, right? So the suction saturation temperature is 51 degrees. The actual line temperature is 61 degrees. 61 minus 51 is 10. So the refrigerant has 10 degrees of superheat, or it is 10 degrees over its saturation temperature. And it's 100% vapor. We know that. Now there are reasons that you might want to check your superheat at your outdoor unit. You might want to see how much extra heat you're picking up on the way there. You might want to see how much that pressure changes. If you had a kink, you could be actually creating another metering device, and you could have a pressure drop / temperature drop and a kink that you had in your suction line. Any questions about superheat before we move on?
No, I don't see any. You're good to go.
All right. So we're going to move on to the compressor. So we could spend an entire hour or more talking about compressors and different types of compressors and how to troubleshoot and diagnose compressors, but that's not really the focus of today's class. I really just want to talk very broadly about the compressor and sort of what the compressor does. So the compressor is a vapor pump. Its job is to pump vapor refrigerant through the system. If we, for a period of time, if we introduce liquid refrigerant into our compressor, you can't compress a liquid. You can compress a vapor, but you cannot compress a liquid. So if we continually feed liquid refrigerant to our compressor, we will kill it. If you've gone out and you've got systems that are on their, second, third, fourth compressor in a short amount of time, there's a good chance that you're pumping liquid, you're sending liquid back to this compressor. So compressor is a vapor pump. Introducing liquid into that compressor will kill it. And so think of the compressor as the heart of the system, right? So it's pumping the refrigerant. Not only is it moving the refrigerant through the system, it's also compressing that refrigerant, because we've got to get the temperature of the refrigerant much warmer than the outdoor ambient air that's going to be pulled through our condenser coil, if we want the heat to move from the refrigerant to the air. So as we increase the pressure of the refrigerant, we increase the temperature. We went over the pressure temperature relationships in part 1. So in this particular diagram here, we have got 371 PSIG refrigerant at about 111 degrees coming out of our compressor, where we had about 145 PSIG or 56 degree refrigerant coming into our compressor. And I thought I had another, there we go. I want to make another note that the suction line continued to gain heat. And I think I got a typo there. I think that should be 66 degrees Fahrenheit and not 56 degrees Fahrenheit. So I apologize for that. So we had 61 degree refrigerant coming out of our coil, and now we've got 66 degree refrigerant. Whoa! Now we got 66 degree refrigerant coming into our compressor. And so we picked up another 5 degrees on the way, and that could have been because we had a very hot attic. The line set was run down the sun exposure side of a house, or any other reason. So if we're checking superheat at the outdoor unit, we're not getting a good reading. Again, I'm sorry, I have a typo here. That should say 66 degrees. Right, so it's time for our first 2 questions. We're a little bit ahead of schedule, which is good. Again, you're going to answer these by going to the chat window, and the first correct answer is going to get it. So what are the 2 types of heat removed by the evaporator coil? I see lots of correct answers.
But there's only one winner, and that is John Manning. He was the first to answer correctly.
Well done, John. All right, so our second question is something. The compressor is designed to pump what? And I'm not looking for a type of refrigerant, but what state of refrigerant is the compressor designed to pump? Lots of correct answers. Wow, lots of correct answers.
Anthony Kaiser is the winner on that one. Good job.
Okay, awesome.
Fast, quick on the draw.
Yeah. All right, so we will move on to the condenser. So in the condenser coil, so here is another, I cannot. Hey, so does anyone know if I go over here more and say leave, is that gonna leave me from the meeting, which I don't want to do. But
Yes.
I don't want to see this. I dock this to the top. All right, Sorry, it's not. Okay, there we go. So we have got a compressor. We've got our suction and liquid lines. We got our service valves. We got our condenser coil, and then we got the tubing that sort of connects everything together, right? So we have got, and these numbers will match up. You can see that I have the correct temperature here of 66 degrees Fahrenheit on our suction line temp, 111 degrees Fahrenheit on our liquid line temp, and then our pressures of 145 and 371. And again, if we don't get the temp of the refrigerant over the ambient temperature, we're never going to remove that heat, right? So if you're only checking your superheat here, and yes, I realize that virtually all modern systems have an expansion valve, and we're going to charge a system with an expansion valve using the subcooling method. But it's also important to check superheat and know what's going on with your refrigerant as it leaves your evaporator coil. Only checking subcooling and not looking at superheat, you're only getting sort of half of the picture of what's going on with the refrigerant in the circuit. It's sort of like looking just at one of your two blood pressure numbers, right? They're separate, but they are they reference one another, or they work together to give you your total blood pressure. It's the same thing with our it's the same thing with our
Wait, I got a question.
yeah.
I see that the suction line temperature on this unit, you have 66. Is there a limit to that suction line temperature that where it can cause harm to that compressor?
Well, it cannot. So the compressor is cooled by the refrigerant, and it won't necessarily harm it, but what it will do is it'll open the limit, right? There's a thermal switch in that compressor, and if the compressor gets too hot, that limit switch is going to open. And most of the time, it's really just like a little bimetal switch. And if we open and close that safety a number of times, it can fail. So, I mean, yes, it can, but there are safeties involved, and really, and I know these numbers aren't necessarily true. I mean, it'd have to be pretty warm outside for you to actually be seeing these numbers that I have here. But I mean, to answer your question, yes, it can, but most compressors have a safety built in to prevent that. So we got high pressure, high temperature, vapor refrigerant coming out of our compressor into our condenser coil. We reject the heat from that refrigerant to the outdoor air. And while the refrigerant is flowing through the tubing in our condenser coil, it's changing state. So it's changing state from a vapor to a liquid, or it's condensing, right? Just like we condense water on the evaporator coil. The same process is happening, changing the state of the refrigerant. And again, the refrigerant has to be 100% liquid when it leaves our condenser coil, because we have to have a column of 100% liquid refrigerant go into our metering device. So as the refrigerant's moving through the coil, it desuperheats, condenses, and then subcools that refrigerant. And again, the subcooling is saturation temp, which we get from looking at pressure, subtracted from line temp. So at 371.5 PSIG, so we got a head pressure of 375.1. Pressure temperature chart shows us that should be 111 degrees, or our saturation temperature for the refrigerant at that condition is 111 degrees. Again, you can see that from your gauge manifold, right? So 371 111 degrees Fahrenheit. We're going to take our gauge pressure. We're going to convert that gauge pressure to saturation temp. 371.5 psig, 111 degrees Fahrenheit. Then we're going to measure the liquid line temperature coming out of our condenser. And in this example, right, so I've got my clamp-on thermometer right here coming out of my condenser coil. It's 101 degrees. So just the simple math of that tells me that, 111 degree saturation temp minus 101 degree actual refrigerant line temp. The refrigerant line temp is 10 degrees cooler than the saturation temp, or I have 10 degrees of subcooling in my refrigerant. And I think I might have glossed over this on my evaporator slide, but if you look here at the condenser coil, you can see that I've got temperature readings sort of all the way through this run. And yes, this is a very simplified coil. So we come into our coil at 111 degrees, and this whole time what we're doing is we're changing the state of the refrigerant. So we're boiling this refrigerant off, and we don't actually start gaining superheat until towards the very end of the coil. So at this point, we've gone from 111 degrees to 108 degrees. And it's right here, somewhere between this 111 and this 108 is where we became 100% liquid. And now we start subcooling the refrigerant. So it really is telling us how much liquid refrigerant, 100% liquid refrigerant do we have in our condenser coil, where superheat tells us how much 100% vapor refrigerant we have in our evaporator coil. If we have any subcooling, we know the refrigerant has to be 100% liquid, and that's super important because our refrigerant going into our metering device has to be 100% liquid. Any questions about the condenser before we move on to metering devices? Okay, so we're going to talk about the purpose of the metering device, which I've already touched on, types of metering devices, advantages, disadvantages, how they work, and how to troubleshoot.
Oh, wait, we have a question here. I don't know if you want to ask, maybe.
Another guy.
Is the scale still between 5 and 20 degrees for the superheat?
So I guess it depends, right? If we're not charging by superheat, I was always taught, just same as David, I was always taught 8 to 12 degrees of superheat is what we're looking for. But really, we just want to see, coming out of our evaporator coil, do we know that we're 100% vapor, right? Do we have superheat? And then checking it again just to see how much extra heat we're picking up. We're not going to charge based on superheat, but we are going to just look at it and make sure that it's present. It looks like there's another question. Every single system. So we're gonna charge, and I have a graphic from a charging chart here later, but we're gonna charge to subcool to a specific subcooling number based on the equipment that we're using and the outdoor temp. So we don't want to charge to subcool based on sort of a rule of thumb. We want to charge to the subcool that our particular matchup shows based on the charging chart.
In the charging the subcool would be more an expansion valve.
Exactly. You're going to charge a system with an expansion valve to subcool. You're going to charge a system with a fixed bore metering device, a piston, capillary tube. You're going to charge that based on superheat. And really, you should have charging charts for both of those. So I would always recommend following the OEM charging chart and not just sort of rule of thumb guessing about your charge. So Fixed bore. This is an example of a fixed bore. This is a piston. And let me get back here. And you can see this piston is a brass part that has a hole sort of milled through the middle of it. And the way that we meter the refrigerant through a fixed bore, and really it's how we meter refrigerant through any metering device. It's just how we get there, right? So if you think about your metering device, let's make an example and say that your liquid line is like a water hose, right? You go outside, you open your hose bib, and you got the hose in your hand. If you put your thumb over the end of the hose, and you start to build pressure, as the water comes out around your thumb, the pressure is dropping and the temperature is dropping in that water. And it's the same thing. The difference between a fixed bore and a thermostatic or an electronic expansion valve is that the fixed bore, being this piston or a capillary tube, they can't change the amount of refrigerant. They can't adjust to the conditions and change the amount of refrigerant that moves into your coil, right? So, or in this graphic, we call it a fixed restrictor. So that's based on the size of the orifice in that piston or the size of the hole that's drilled through that piston. And as you can see, the only way to change the amount of refrigerant that's being metered through that metering device is to change the piston with a larger hole in it. So you get what you get. It's very simple. For a long time, they worked great. They don't really allow us the ability to hit efficiency numbers that we need to hit in modern equipment. So that's why you don't see a lot of pistons out there. Are they out there? Yes. Is the industry moving more and more towards expansion valves? Yes. Which brings us to the thermostatic expansion valve, or TEV or TXV, right? So here's a graphic of or a picture of an expansion valve. And the breakdown of this valve is, so all the valves that we use are set at the factory. We don't use any adjustable valves. An adjustable expansion valve is pretty common, say on the refrigeration side of things, or even, you can buy expansion valves that will allow you to adjust the superheat, which is sort of what this pin down here does. But overall, for your expansion valve, you've got a power head, which, let me go back to the previous slide. The power head, which is attached to a sensing bulb. This sensing bulb is filled with refrigerant, and typically it's the same refrigerant that is used in that system. Not always 100% of the time, but the vast majority of the time. Then we've got some push rods that push down against a pin, and that changes the size of the changes the amount of refrigerant that's metered into the evaporator coil. Okay, so again, here's our expansion valve. There's the power head, and then you can see in this graphic that coming from the power head, inside the power head, there's a diaphragm, and I have a drawing of it. There's a diaphragm that flexes based on pressure. So we've got the pressure from the sensing bulb pushing down on the power head, diaphragm of the power head. That pushes down on that push rod, which pushes down on this pin and changes the size of this gap here. And that's how the expansion valve works. We've got a power head pushing against a spring, and that pressure differential is what changes the size of essentially what our orifice would be, right? Or the gap that our refrigerant is being metered through. So we've got our sensing bulb, which is going to the top of our power head. You can see this black line right here that shows the diaphragm. So this pressure in on the top of the diaphragm is pushing against the combined pressure of this equalizer tube, which is tapped into the suction line, right? So we've got essentially superheat here, saturation temp here, and this spring. So the spring and the equalizer line push against the bulb temp. So the hotter the suction line, the hotter the sensing bulb gets, the harder this pressure pushes down, and the more refrigerant flows through the valve. And this is a pretty good sort of representation of how that valve works, right? So you see the green is the bulb pressure, the blue is the suction pressure, and then we've got the spring pressure down at the bottom. And the spring and the suction pressure are pushing against the bulb pressure. And as the bulb gets warmer, the pressure in that bulb and the transmission tube coming from the bulb, harder that pushes down against the power head. So the beauty of the expansion valve is the hotter it is inside, the faster we can drop the temperature. We can feed more refrigerant into the evaporator coil. The hotter it is inside, we can boil that refrigerant off, right? Where we're changing the state of the refrigerant, we're removing most of the heat. And then as the temperature starts to lower inside, the pressure on our bulb becomes diminished, and we close up our expansion valve a little bit more. So we're constantly measuring, comparing, and adjusting, right? So this is like a PID loop that's happening here, right? So we're constantly evaluating, we're making adjustments, we're evaluating, we're making adjustments. And that's why expansion valves is so much more efficient than a fixed bore or a fixed restrictor metering device. Any questions about how the expansion valve works before we go into troubleshooting it, and then on to system charging and some other things?
You don't need to adjust these expansion valves, correct?
No, these are non-adjustable expansion valves. So the sensing bulb on your valve needs to be mounted at 10 o'clock or 2 o'clock on your suction line. And it's real important that the sensing bulb is mounted in a nice, smooth, clean, flat section of that copper line. And it's really important that you use the mounting hardware that comes with the valve. If you walk up to a system that has a expansion valve on it, and you can grab that valve with your hand and sort of rock it back and forth, it's not tight enough. It's not locked down onto that suction line tight enough to get good transfer, right? So the temperature of the refrigerant in the suction line is transferred into the refrigerant in the bulb using conduction, right? And if this isn't tight, or you mount it on a turn, or you mount it on a braze joint, it's not making good enough contact with your suction line for it to really be the same temperature as the suction line, which it should be. It should be insulated really well. It should not be strapped on there with, here's a great example of how not to mount expansion bulb or a TXV bulb. This one's A, it's wrapped with electrical tape. B, it's on the outside of the insulation. So this is only reading really the ambient temp in wherever our this coil is.
Hey, Wade,
Yeah.
we have a couple people that keep raising their hand, and we don't really have a way of giving them an option to talk. So I just wanted to make an announcement that if you have a question, just put it in the chat because we don't have a way of talking to you with the hand
Okay, yeah,
raised.
good point. If you want to ask a question, make sure you type it in the chat, and don't raise your hand. So I have seen expansion valves in many different various and different situations like this, right? Where it's either just hanging loose or somebody strapped it with a couple of zip ties to a line. It's not insulated well. Anything like that is not allowing your expansion valve to operate properly. If you need to troubleshoot an expansion valve, it's a real simple way that you can do that. So if you disconnect the expansion valve bulb and disconnect the sensing bulb from the suction line, and you can either put it in, hold it in your hand, you can put it in a cup of ice water, you can put it in a cup of warm water. If you change the temperature of that bulb, it's going to change the way that the valve drives, and you will see a pressure change and a superheat change. And so if you think that your valve's not responding, or you think you got a dead valve or whatever, if you just do that, disconnect it, hold it in your hand for a little while, and take a look at your pressure or your temperature. Now, it can be hard to be in two places at one time, right? If you're working by yourself, you're not going to be able to hold on to that valve and then run outside and look at your gauges. You can put it in a cup of warm water and give it a few minutes, and then walk outside and see if that changed your suction pressure or your superheat.
Wait, I got a couple comments here.
Yeah.
One was, can you emphasize if there's importance with the tail end, the clipped end, whether it should be up or down, especially in the vertical application?
Oh, okay, yeah. So let me go back to a graphic there. Whoa. Right. So this tail end here. I was always taught that this actually should be inverted. So what we want is, we don't want the liquid and or the liquid refrigerant that's in here. We don't want it to just easily flow down here and sit in the power head, right? We want that liquid refrigerant to be here in this bulb. So if I was doing that, I mean, there's obvious other problems with the way that the sensing bulb is installed, but I would flip this 180 degrees and have the tail coming out of this side, pointed up in a vertical application.
And then the other comment is more of, I guess, a engineer design, as far as why the choice of a round cylinder versus something that would contour to the copper piping, maybe like a half moon shape.
That's a good question. I would imagine that because you have various line sizes, right? So if you look at line sizing charts, you might use 3 or 4 different sizes of suction line or liquid line that would be acceptable. And if you did that, you'd have to have a different bulb with a different sort of concave shape for each line set to really get a good connection there. That's my assumption.
And then what about location as far as distance? I mean,
So as close to the external door of that coil as you can get it. Within 6 inches is great. I mean, if you take a turn and go, like in this example here, there's not enough room to put it right here because we've got a turn. So location wise or distance wise, this is probably fine. But I'd want to flip it 180 degrees. And you can't get too far because the transmission line or the capillary tube that comes out of that bulb is not really long. Another thing that you want to think about when you're mounting your bulb and you're servicing or you're diagnosing a TXV, if you bend that piece of tubing too many times, you could fracture it. And if this piece of tubing springs a leak, you're gonna lose the refrigerant charge that's in the bulb, and the TXV is gonna slam closed, right? The spring and the suction pressure are going to push that thing closed because there's no bulb pressure counteracting that, pushing back down on it to open it up.
And any recommendation versus like if you have space on the inside, not to do inside? Is there any reason why it wouldn't be okay?
It really depends on the design. You know, we used to have coils that had expansion valves mounted inside the coil box. But if you do that, you're really not necessarily getting the temperature of that line. You're getting also the temperature of the air inside the coil box itself. So I would just say follow OEM regulations. And like I said, we used to have some coils that had expansion valves mounted inside the coil box, but I don't think we have any currently that are spec'd out that way.
I think we had issues in the past where when they were in the inside unit, they were left on and they were overheated when they were soldered.
That is true. I've seen that many times. Yep. Okay, so we got another quiz, and then because we're running a little bit early, I'm going to talk a little bit about charging, but we're going to go ahead and do these two quizzes. So we got 2 questions. Get your chat box ready. Question number 1, what are the 2 devices or the 2 components that separate the high pressure and low pressure sides of an air conditioning system? Chat notifications are going crazy.
Okay, first correct answer that I see is David Toombs. Congratulations, David.
And then our next question, final question is, what does the abbreviation TEV stand for? That should be easy.
All right, Spyro is the winner on that one. I apologize, Spyro, I can't pronounce your last name, but we will make sure that you get the prize. So there's 4 winners this time around, and what we'll do is we'll notify you. We'll have you pick up your prizes at the closest branch to you.
Okay, all right. So we talked about.
Wait, I think there was a question before we started. Before we started this quiz thing, so let me scroll back in there and see what we have.
There was one was about the RBHP where the expansion valve is mounted inside, which is correct. The on the
Okay, yeah, and I try to not say like absolutes, like we don't do that, because invariably when I do, somebody reminds me of, oh, what you actually do on this one. So that I appreciate that. Yeah, we do.
And then the other one was, for instance, like in a hot attic, the expansion valve being mounted on the outside where it's a hot attic, wouldn't it be more beneficial to mount it on the inside? But I guess my answer to that is, if it's insulated with the copper, that hot attic shouldn't be an issue, correct?
Absolutely. It's crucial that it gets insulated. You can't really insulate it too much. So I always used to use the insulation that came with it And I'd also cut me a couple pieces of Armaflex to add to that insulation, because you can't over insulate your valve really. All right, so evaporator. We're just going to recap really quick. Evaporator. The job of the evaporator is to absorb heat from the conditioned space. And remember, we can't create heat. We can't destroy heat. We just move it around. So that's what we're doing in the evaporator. We're absorbing heat. The compressor, we're pumping the refrigerant, and we're increasing the pressure of that refrigerant so that when the refrigerant goes into the condenser coil, it can reject the heat. We're taking the heat from indoors, and we're pumping it and pushing it outside. And that's one of the things that is really cool. I got another typo there. There's another thing that's really cool is like when you walk over to a condenser and it's running, and you put your hand over it and you feel that hot air coming out of that condenser. That is the heat energy that was absorbed inside and then pumped outside and rejected. I just think that's really cool. The metering device decreases the pressure in the refrigerant so that we can then absorb the heat in the evaporator. And just as simply put as I can, superheat is when the refrigerant is warmer than the pressure temperature chart says it should be. And subcooling is when the refrigerant is cooler than the pressure temperature chart says it could be. And sometimes those two terms can get confusing, especially if you haven't been in this trade for very long, because if you look at the superheated line, right, which is your suction line coming out of your evaporator, and you're outside and you grab onto that line and you feel it, it feels cold, right? It feels cooler than your body temp, because it is. But when we talk about warmer and cooler, they're just relative terms. So yeah, the temperature of that refrigerant is cooler than your body temp, but it's still hotter than the PT chart or the pressure temperature chart says it should be. The same thing with subcooling. The liquid line coming out of your condenser feels warm typically when you grab it with your hand, but it's cooler, or it should be. If it has any subcooling, it's cooler than the PT chart says that it should be. So don't get caught up in, hot or cold or warmer or cooler. It's just we're comparing the temperature of the refrigerant to what the saturation temp is, or what the pressure temperature chart says that it would be. We're going to talk a little bit about charging. I'm going to skip over this Q&A. We're going to talk a little bit about system charging. I want to preface this by saying that don't ever put your gauges on a unit or start charging a unit before you verify airflow. The charging charts that I'm about to show you are all built on the assumption that the indoor airflow is correct. And depending on what that system is, or depending on that matchup, it might not be 400 CFM per ton, which is what we were all thought, right? It was beat into my brain when I first started doing this, 400 CFM per ton. Well, that's not necessarily the case, right? So we got to make sure that we know what that rated airflow is, check it, which will be in class number session 4. We got to know what the rated airflow is. We got to verify that rated airflow, and then we can charge. If we're not moving the right amount of air through our evaporator coil, the charging chart is irrelevant. It's useless. It's not telling us anything. So even still, a lot of people want to use their optimum temperature comparison device and their superheat confirmation sensor to check to see if their suction line is beer can cold, and then the system's charged and they're good to go. You're overcharging it. So here's an example of a RA14 charging chart. This charging chart is available on PTS in myruud.com. If you do not have a MyRuud account, get with your folks at Tropic Supply and they'll get you hooked up with a MyRuud account. Couple things before we just dive right in. Usually when people look at the charging chart, what they see is these sort of three tables on the left, right? Right here is what people really concentrate on, but there's a couple things that I want to bring up but before we dive into that. And that's over here in the notice section. The first thing that I want to really point out is that if the system's not running when you get there, if it's satisfied when you get there, A, you got to turn it on and you got to check airflow. So it needs to be running. You need to check airflow before you validate your charge. So it should have been running for a few minutes before you even go out there and start messing with your charge, because you got to verify airflow. Indoor conditions, right? So there's two different parts of our chart. There's the gross charge and then there's the final charge. For gross charge, we need to be within 2 degrees of 80-degree dry bulb inside. So our indoor temp, when we're doing our gross charge, needs to be 78 to 82 degrees. If it's not between 78 and 82 degrees, you're not going to be able to finalize, or you're not going to be able to really dial this gross charge in at all. If the system hasn't been running, or it's a change out and it's 92, 95, 98 degrees inside, you're going to have to let the system run for a little while before you even mess with the charge. For the final charge, or our subcool number, your indoor temp needs to be between 70 and 80 degrees in order to set your final charge. If you think that you're gonna be able to dial your subcooling number in based on what the charging chart tells you, and it's 90 degrees inside the house, you're gonna overcharge the unit. No ifs, ands, or buts about it. Sometimes that means that you might have to take a break. You might have to button everything up out there at that job before you start setting the final charge. Or you might have to come back tomorrow to really get it right. Right? So here's the part of the chart that everybody looks at. We've got our matchups, right? So here's our outdoor unit model number at the top. This is for all coils, multi-position. So you may see some charging charts that specify, somebody mentioned the RBHP earlier. You might see a charging chart that specifies a particular coil or air handler, right? Or downflow, horizontal left, upflow, horizontal, downflow, horizontal right, upflow, horizontal left. But for this example, it's all coils that match with this unit, all positions. And right, so we're going to look at the 1436 at 95 degrees. Our gross charge should be right about 383 psig on the head pressure and 137 on the suction line. But again, that is based on an indoor temp being plus or minus 2 degrees from 80 degrees Fahrenheit inside. For our final gross charge, indoor temp needs to be between 70 and 80. And at 95 degrees, for that matchup, we want to charge this unit to 15 degrees of subcool. Now,
I got something wants to, I guess, slow down for a second. It says, please go over the reason for gross charge when the subcool method is the final charge.
So your gross charge is allowing you to just sort of get the system close. You're not gonna charge based on this gross charge number. You're not gonna just leave it forever based on this gross charge number. But as the system's running, you can see that you're close to these numbers. It tells you that at 95 degrees, I'm at 380 and 140. I'm probably pretty good. I'm gonna leave this system to allow it to cool the space so that I can come back. It really is just sort of a verification that you don't have anything wrong with your expansion valve, your refrigerant tubing, anything like that, right? So this is just sort of a heads up. This is where you ought to be, but this is what you're going to charge to. You're not going to pick one or the other. You're ultimately going to charge to this. This is just your maybe your step one. I hope that answers your question.
In that temperature on the left of the chart, that's the outdoor ambient or indoor?
Outdoor ambient temperature. Yep. So at a 95-degree outdoor temp for our RA 1436, our gross charge is 383 and 137, but our final charge at the same outdoor temp, we want to charge to 15 degrees subcool. Any other questions about that? That's the last slide I have on charging.
Somebody was saying, should the subcool not always be 10 degrees Fahrenheit?
No. Subcool is going to be set by the by engineering. So the rule of thumb that you should always charge to 10 degrees subcool. In some situations, that's right? So if we look at this 1448 at 95 degrees, we're calling for 10 degrees of subcool. And a lot of that has to do with the size of coils. It has to do with indoor and outdoor temp. But these charts are built by the engineers, and they're designed to get you exactly where you need to be so that the system is operating at the capacity and the efficiency that it's rated at. The vast majority of systems that are out there that have been installed and are out there in the world are not operating at capacity or at rated efficiency because of a lot of things. Airflow and incorrect charge are two of the major reasons that most systems out there are not operating as well as they could or should be.
And then as far as where to measure the subcool, it would probably be better to measure on the inside right before the expansion valve. And then it's about a 1.5 degree plus or minus is fine.
So you're going to measure your subcool at your outdoor unit. I'm going to go back. Now I'm going to ride back quite a few slides because I got a graphic here that shows exactly where you're going to measure. So you're going to measure your subcooling right here, right? So you're going to look at the liquid line pressure. You're going to convert that liquid line pressure to saturation temperature, and you're going to take your thermometer and you're going to strap it or clamp it here on your liquid line. Because what we want to, just like with our evaporator superheat, we want to know when we're checking subcooling, we want to know exactly how much liquid refrigerant we have sitting here in our condenser coil. Now that doesn't mean that you can't also check it right at your expansion valve if you're troubleshooting. But as a general rule, that chart is built on checking it right here at the outdoor unit. And it's real important, just like with your sensing bulb, having a really good connection to your line. If you don't have a really good clamp on or a really good K-type thermocouple to check this temperature, you're not going to get a good line temp with a infrared thermometer or with like a stick thermometer that you're going to tape on there. You've got to have the right tools to really check this. Excuse me.
Is there anything that would inhibit the getting a full line liquid to expansion valve, such as restrictions? Or I get some calls and fail TXV, and sometimes there's that screen before the expansion valve.
So yes, that all those things could happen, right? So if there's a screen before the expansion valve and that screen gets clogged up with any sort of material, a lot of times it's copper oxide. If you've been to any of my classes before, I've talked about raising with nitrogen and sort of mitigating the presence of copper oxide in your refrigerant lines. That can clog it up. If you got a kink in a liquid line, that is going to act as a metering device before you get to your metering device. And one of the biggest things that can cause you to not have a column of liquid at your metering device is having a kink in your liquid line.
And one other question, sorry. So these are going overall split systems. How much would change, or what would change if it was a package unit?
Same thing. You're gonna consider everything the same way. You're gonna measure everything, a little in different locations, just because of the differences between a split and a package unit. But you're still gonna check your suction line temp when you're reading superheat coming out of that evaporator cooler, coming out of that indoor cooler. Any other questions? I'm going to go ahead and just zoom up to the end of the.
Yeah, I got one more question. Say for instance, you've changed the compressor. What would be your recommended way of recharging the system?
So first, just you'd weigh the factory charge back in. So let me make a point about the factory charge. There are situations where when you install a system, that factory charge might be a little bit too much based on whatever line set you have, or what the conditions are, or what that exact the application is, right? Every single job is different, and don't assume that you've always got to add refrigerant. Sometimes you might not need to. Sometimes the factory charge, you might need to pull out a couple of ounces. But if you're replacing a compressor, you're going to weigh the factory charge back in. You're going to let the system run for a while, and you're going to charge it based on what kind of metering device it has. Does it have an expansion valve, or does it have a fixed bore? If it has an expansion valve, you're going to charge it based on the subcooling method. And if it has a fixed bore, you're going to charge it based on the superheat method. And that should all be available in the specifications, or in the instruction manual, or in the OEM data for that.
And then looks like I have a last question here. Is elevation does it play a factor in charging a system? I mean, not in Florida because we're flat, but maybe further north.
No, not really. It doesn't. You're gonna base that charge on the charging chart. You're not really gonna worry about your elevation. If that's the question that was being asked, it shouldn't matter.
I think they're talking about what they're talking about is vertical rise. I guess like when you have a condo, maybe 10, 12-story condo with the air handler, maybe it's on the second floor and the condenser's on the roof.
So as long as your refrigerant line and tubing is within the line set specifications, you'll be okay.
And what about humidity? Does that affect the subcooling at all?
It has a lot more of effect on superheat than it does on subcool. What really affects both of them is indoor temperature not being, between 70 and 80. And that's one thing that you can do, right? So you can have a system that either the airflow is not right, or the indoor temps are not where they need to be. You can measure and charge that system to that amount of subcooling, right? If it says 15, you can charge it to a 15-degree subcool. But then when you come back if/when you come back later, it may be way off because it was 95 degrees inside when you charged it. Right. And that's the thing that happens. That is the thing that happens a lot. And before I really understood that, I've done it many times. If there's a wrong way to do it, I've done it wrong. But that doesn't mean that I'm okay with doing it wrong, right? It means that I learned something and now I know that that's not the right way to do it.
You're not alone.
I mean, we all do, right? Anybody that tells you that they know everything and they don't make any mistakes, I would be hesitant to believe them. All right. Well, thank y'all for your time. I appreciate it. I don't see any more questions coming in.